Rankine cycle, and this Rankine cycle is considered to be as an ideal vapor power cycle. Before going into the concept of Rankine cycle, first let us discuss about the steam power plant. This is the steam power plant and it consists of a boiler, turbine, condenser and a feed pump. Dry saturated steam from the boiler enters the turbine at a pressure P1 and T1, and this dry saturated steam gets expanded in order to produce the work WT. That is, this dry saturated steam which is entering the turbine gets expanded in order to produce a work WT. Since it is being expanded, the pressure gets reduced. That is, the pressure at the point 2 is less compared to that of the pressure P1. And this process is taking place isentropically and the temperature T2 remains constant, and this temperature T2 is the saturated temperature for this condenser. Therefore, the pressure P2 will be much less compared to that of P1. Since it is an isentropic process, no heat is being rejected out of this turbine. That is, this turbine is being entirely sealed. That is, no heat is being rejected out of this turbine, and the work done by this turbine is given as H1 minus H2. Since the turbine is a work producing device, and this equation H1 minus H2 is being formulated from SFE equation. Okay, and this dry saturated steam after crossing this turbine gets converted into a wet steam, and this wet stream enters the condenser at a pressure P2 and temperature T2, and it being converted into water. That is, this wet stream is being converted into water by the condensation process which is taking place in the condenser, and a heat QC is being rejected from this condenser, and this heat QC is nothing but the latent heat of the steam, and the heat which is being rejected from the condenser is given as H2 minus H3. And again, this equation is being formulated from steady flow energy equation, and there is no change in pressure. That is, this condensation process is taking place at constant pressure and constant temperature. That is, P2 will be equal to P3 and T2 will be equal to T3. That is, there is only a phase change which is taking place in this condenser. That is, the wet stream is being converted into water, and it reaches the pressure P3 and T3, and pressure P2 and P3 are equal and T2 and T3 are equal. Then this water is given to a feed pump where the pressure is being drastically increased isentropically. That is, there is an isentropic compression process which is taking place in the feed pump, and a work, in order for this compression, a work WP is given to this feed pump, and the work WP is equal to H4 minus H3. Okay, the work which is given to the heat pump is H4 minus H3, and this work given to the heat pump or this feed pump will increases the pressure of the water, but the temperature remains more or less same. That is, there won't be much difference in the temperature, but the pressure will be drastically improved. That is, P4 will be much greater than P3. Okay, and this highly pressurized water is given to the boiler, and in the boiler the temperature of the water is being raised and it is being converted into a dry saturated steam. That is, in the boiler the temperature of the water is heavily increased by the heat addition QB. That is, a heat which is given to a system or this boiler in order to raise the temperature of the water and make it as a dry saturated steam by maintaining the constant pressure. That is, the pressure remains constant but the temperature increases. That is, T1 will be much greater compared to that of T4, whereas pressure P4 will be equal to P1. That is, at constant pressure, we will be rising the temperature of the water. Due to this, there will be a change of phase from liquid to saturated liquid to dry saturated steam. Okay, and the heat which is given to this boiler will be equal to H1 minus H4. Okay, the heat which is given to this boiler will be H1 minus H4. Okay, and again this dry saturated steam is given to a turbine and this process continues. That is, there will be a cyclic process which will be taking place. There is a work done by the system which is by the turbine, and the work which is done to the system for a feed pump, which is nothing but the centrifugal pump, and there is a heat rejection and there is a heat addition. That is, heat rejection is to the condenser and the added is to the boiler. From this you can say the work done by the turbine is greater than the work given to the feed pump, and from this W net will be equal to WT minus WP. That is, the work produced by the turbine is much greater than the work given to the feed pump. Therefore, at certain point this may be neglected. Okay, and the heat which is given to the system and the heat which is being rejected from the system is considered to be as the net heat, and the net heat is given as Q of N will be equal to QB minus QC. That is, the heat which is given to the boiler is more compared to that of the heat which is being rejected from the condenser, and the efficiency of the system is given as Wn divided by QB, where Wn is the net work done and QB is the heat which is added to the system. From this, the efficiency can be written as 1 minus QC by QB, where QC is the heat rejection and QB is the heat addition to the system. And now we can represent this steam power plant in the TS diagram. Okay, you can represent this in the TS diagram. Consider this at the state point 1. State point 1, where the steam is at a dry saturated steam. That is, it is a dry saturated steam. And in the turbine, this dry saturated stream gets expanded isentropically. That is, the process which is being taken place is an isentropic process. Therefore, entropy of the system remains constant. That is, the entropy of the system remains constant. Okay, that is from 1 to 2, where work is done by the system, and from 2 to 3, that is, from 2 to 3, the pressure remains constant. That is, heat is being rejected at constant pressure and temperature. That is, the temperature and pressure of the system remains constant, whereas heat is being rejected from the system, which is the condensation process, and QC is nothing but the latent heat of steam which is taken away from this condenser. Therefore, this is a constant pressure process. From 2 to 3, where in this process the heat is being rejected from the system. Which is considered to be as QC. And again, in the feed pump, the water is being isentropically compressed. That is, a compression process which is taking place through an isentropic process. Therefore, entropy of the system remains constant. Therefore, from 3 to 4, the entropy of the system remains constant. This is 3 to 4, where the entropy of the system, the entropy of the system remains constant. This is 3 to 4, where work is done to the system, which is nothing but WP. And from 4 to 1, that is from 4 to 1, the heat is being added to the system. This is the heat is being added to the system, that is to the boiler, which is nothing but QB. Okay, that is from 1 to 2. It is an isentropic process, that is isentropic expansion. From 1 to 2, it is an isentropic expansion where the turbine produces a work WT, and from 2 to 3, it is a constant pressure process where there is only a phase change which is being taken place. Therefore, it is a constant pressure process. And again, from 3 to 4, there is an isentropic compression. Therefore, entropy of the system remains constant from 3 to 4. And again, from 4 to 1, the heat is added at a constant pressure. Okay, heat is added at a constant pressure to the boiler. This is the TS diagram, or the representation of the steam power plant in the TS diagram. Okay, at the state point 1, it is a dry stream, and at the state point 2, it is a wet stream, and at the point 3, it is a saturated liquid, which is nothing but water. Okay, and there is a constant pressure process, that is the pressure of this is equal to constant. This is constant pressure process and constant pressure process, that is heat added and heat rejection is of constant pressure process, which is from 2 to 3, and this is from 4 to 1. Okay, from 4 to 1 and 2 to 3, these two are the constant pressure process, that is the pressure remains constant in this process. And 2 to 3 is the condensation pressure, and 4 to 1 is the boiler pressure. This 2 to 3 is the condensation pressure, and 4 to 1 is the boiler pressure. Okay, now we can represent this in the PV diagram. Okay, we can represent this same process in the PV diagram. Consider this as the state point 1. Since it is being isentropically expanded, it is being denoted like this. Therefore, this is from 1 to 2, and 2 to 3 is a constant pressure process. 2 to 3 is a constant pressure process, and 3 to 4 is again an isentropic process, that is this is the isentropic compression process, that is the process is taking in such a manner or such a fashion, that is it is an isentropic compression process, that is from 3 to 4, and again from 4 to 1, heat is being added at a constant pressure process. Okay, this is the constant pressure process. Okay, you can see the in this process the pressure remains constant and the pressure remains constant, whereas in this case the entropy remains constant. This is entropy remain constant and entropy remains constant. 1 to 2 is nothing but the work which is done by the system, that is done by the turbine, and 3 to 4 is the work which is done to the feed pump, and 2 to 3 is the heat which is rejected from the system, which is nothing but QC, and 4 to 1 is the heat added to the system, that is to the boiler, which is considered to be as QB. Okay, this cycle is considered to be as the Rankine cycle, and this Rankine cycle is the ideal cycle. That is the process 1, 2, 3, 4. That is the process which is taking place as from 1 to 2, 2 to 3, 3 to 4, and again 4 to 1. This is a cyclic process, that is from 1 to 2, 3 and 4, and this process which is taking place is considered to be as a cyclic process, and this cyclic process is considered to be as a Rankine cycle. This cyclic process which is being taking place is considered to be as a Rankine cycle. This is considered to be as a Rankine cycle, and this is the ideal cycle for the steam power plant. This is considered to be as an ideal cycle for the steam power plant. Okay. Now we can derive the efficiency of the Rankine cycle. Okay. Now let's derive the efficiency of the Rankine cycle. Generally, the thermal efficiency is given by W net divided by heat added. This W net is nothing but Wt minus Wp divided by Q of B. And we have find out that Wt is equal to H1 minus H2. Wp is H4 minus H3 divided by Qb is H1 minus H4. Okay. This Wt is taken from here. This is Wt. This is Wp. That is the work which is given to the feed pump. And the heat added is given as H1 minus H4. Okay. This is the thermal efficiency. This is the thermal efficiency of the Rankine cycle. And it is given as H1 minus H2 minus H4 minus H3 divided by H1 minus H4. Okay. The work which is done to the the work which is done to the pump is very negligible, so that the value of H3 can be equated to H4. That is, this H4 is equal to H3 since work done, that is the pump work, is being neglected. That is, the pump work is being neglected. That is, the work the turbine is being produced is much higher than that of the work which is given to the pump. Therefore, we will be neglecting the pump work. Therefore, the enthalpy or the efficiency equation, that is the thermal efficiency, is given as H1 minus H2 divided by H1 minus H4. That is, this entire term gets neglected. Therefore, the efficiency is given by the difference in enthalpy at state point 1 and 2 by the state point 4 and 1. Okay. This is considered to be the thermal efficiency of the Rankine cycle.